Dipanjan is going to tell us about Jet-ISM interaction in early type galaxies. Looks like we're back on simulations.
Yes. So, good afternoon, everybody. I know this is the fag end of the conference, and everybody's tired. So I promise not to show any equations and nice, colorful movies to keep you awake. So I'm Dipanjan Mukherjee, a postdoctoral fellow at ANU, working with Jeff Bicknell, Ralph Sutherland, Alex Wagner, and Rob Sharp, and trying to understand how jets affect the host galaxy. So this is feedback in a different context. In the early morning sessions, you heard about feedback at larger scales. But what we are trying to look at is how feedback affects the local environment of the galaxy. And I would like to thank the speakers before me for giving a nice motivation for the kind of simulations I'm going to present in the observational sense. So the main goals that we have been trying to understand is the jet cloud interaction in a scales of few kiloparsecs near the central source of the galaxy. And dispersal of the warm gas. So once a jet goes through, does it just punch its way through and just like a small region of funnel through? Or does it really affect the entire gas and lifts up the gas? And how much of the gas is actually pushed out of the galaxy? And then what kind of observable signatures would have in optical, X-rays, and radio? And can we predict something from the simulations which we can then compare with the observations? So the previous work, these things have also been flashed by the previous speakers. So Jeff and Alex had done simulations in 2011 and 12 about the Jet-ISM interaction. But in their simulations were small box sizes of 1 kiloparsec. The clouds were static and didn't have any gravitational potential. So in the new work that we have done, we have updated this. We've added gravitational potential, a lot more physics, and most moving clouds mimicking the dispersion that you have in actual galaxies in high redshifts, and of course larger scales. So we've done new 3D relativistic hydrodynamic simulations with Pluto code. And the domain sizes we've been considering is around 5 kiloparsec with the highest resolution at 6 parsec near the central region. Well, we have put in prescriptions of the gravity following the dark matter and baryonic potentials, and also putting thermal cooling from atomic cooling from Ralph's new code, Mappings 5, which will be hopefully published soon, which will be updated on the Ralph, the Sutherland Topita cooling functions. Okay, so this is how we set up the simulations before I start off the movie. So what you're seeing here is a slice through the central domain of the box. And what we have set up is a two-phase medium. It's a hot halo surrounding this gaseous medium. And this is this warm clouds of gas, which is a kind of spherical distribution and distributed over a central region of 2 kiloparsec, which kind of mimics the kind of gas content you'll have in high redshift galaxies, which are rich in gas. And we've set it up as a fractal medium. And for this kind of simulations, what we did is, over and above the fractal turbulent density distribution, we've also imposed a turbulent velocity distribution. So once we let it run, what we find is that these clouds interact with one another, and then they shear and form this filamentary structure, which is very common in turbulent simulations, which you have. So they don't really settle down all. Of course, the turbulence is going down, but they don't really fall down. They kind of virialize in the halo of the potential. So what we do is we start off with a little higher velocity dispersion and let it cool down a bit, and they form these filamentary structures, and then we let our jet through this turbulent filamentary structure. So now the jet goes through. So this is the pressure, and everything is just a slice through the central medium, and this is the density. What you firstly see is the jet is not really just punching this way through, but it's actually moving the gas on the sides as well. And the amount of gas moved on the sides is around 2 kiloparsec from the center. So, I'll let it run once more. So it forms kind of a spherical uniform bubble, energy bubble. And it's not just a region along the jet, but the entire thing inside the bubble is getting affected by this jet that is driving this bubble and then finally escapes. So we've done various kinds of simulations of various jet power, various density configurations, and tried to see what the effects are. So this, what I'm plotting here is the high density clouds only, and this is the temperature. So what I wanted to show was that although the jet is driving the gas and dispersing the gas, not everything is being driven out of the galaxy, as was shown by Katie earlier. So a lot of the gas actually remains within the potential of the galaxy. I'll just let it run once more. So the dense cores of the gas gets stripped a bit, but they remain within the potential. So this is temperature. So as the jet drives this energy bubble, it heats up the gas. So this is a high temperature region within the energy bubble. And it really produces a lot of turbulence inside the cocoon of the gas. And so this would lead to momentary quenching of star formation for a few mega years or so before the gas starts cooling down again. And what I'm plotting here is the density histogram, and the different colors correspond to that jet at different heights. But you can see the density histogram is not really changing too much. So which goes to show that this picture, naive picture that people have, that once the jet turns on, it just drives out all the gas and then stops the feedback, that's not really true, because once you have an inhomogeneous medium with dense clouds at one point and less dense clouds at other points, so the jet really finds a flood channel kind of way. It seeks out the lowest density and then escapes, while the dense cores really remain within the potential of the galaxy. And now what I'm going to show is a jet going through the same medium but with two different powers. So this one is a jet of power 10 to the power 45 ergs per second, and this one has 10 to the power 44 ergs per second, and is significantly different. The first difference is, of course, it will escape much faster, and this is really frustrated, as in the typical CSS GPS community is called the frustrated AGN. So this guy is really frustrated, and it can't really escape, and it takes a long time to even reach 2 kiloparsecs or so. And finally, of course, it will break out. The first thing to notice is that both of them have evacuated some cavity along the stem of the jet, but the amount of region evacuated by the low-power jet is much larger. So low-power jets couple more with the ISM because they stay trapped within the ISM for a longer time. This will become more apparent when I plot the density histogram once again for these two guys. And what you can see for the high-power jet, there is some change because the high-density cores get sheared a bit, but not too much. But for this one, there is a large amount of change. So these different colors correspond to the jet at different heights. So so for the low-power jet, it really strips the medium for a large extent and also affects the medium over a larger extent. And if you look at the luminosity functions, lower-power jets are more ubiquitous. So a low-power jet will be more efficient in affecting or pumping in turbulence into the localized medium, as opposed to a high-power jet, which will just punch and drill through. Yes, and well, we've been hearing a lot about cold outflows. So what I'm showing here is the density plot. This is the temperature and the velocity. And what I'll show is once the jet drives this bubble, the bubble compresses the gas and pushes it outwards along the bow shaft. And this bow shaft pushes this material and then compresses it. And if you look at this circle over here, you'll find that a high density region is created as it pushes and compresses the gas. And initially the gas is heated up because of the shock wave. And as it is high density, it has higher cooling rates, and it starts cooling down. Soon enough, it starts cooling down. So initially the shock wave heats it up to say 1,000,000 Kelvin or so, but over this region, it's starting to cool down below 10 to the power 5. It's a high density region, but here, if you calculate the velocities, it's still going at several hundreds of kilometers per second. So this is like around 400 kilometers per second. So in this way, we've been seeing a lot about cold molecular outflows. So one way to do that is you push the gas, but you also compress the gas and due to this inhomogeneous medium. And then as it compresses, it retains the terminal velocity and starts moving outwards with the cold gas. So from our cooling functions, we can also simulate the synthetic luminosity profiles due to various transitions. We've picked out two, H alpha and oxygen 3. So what I'm showing here is without the jet, when the things relax, so you kind of have a H alpha halo due to the interaction of the clouds. The clouds heat up a bit due to the cloud-cloud interaction and driving shocks within the clouds. And you don't have much emission in oxygen 3 initially. But when you let the jet go through, the oxygen 3 lights up like a Christmas tree because of the bow shock. So this is getting quenched because it's the jet material, which is very hot. But H alpha gets quenched because it falls outside the region of emission of the H alpha. But also you have this dense, But you also have this dense clumps here, which starts to glow back in H alpha as they start cooling down. So if you see, and also these are X-ray profiles for different, just two waveband, and just to show that along the sides of the cocoon of the jet where you have shock-excited gas, you'll also have strong X-ray emission as well, which was also shown by Ralph Sutherland and Bicknell in 2007. So the point to show is that if you catch a jet, young radio jet evolving through a dense medium, you'll have strong shock-excited gas from the sides, which will be a good indicator of a jet driving through a dense medium. Now, these are all fine. These are all fine. So how would it actually look like in observations? And what about the line profile? So ANU is building the IFU of the GMT, and we've been working with the instrumentation guys. And what we do is we take our simulation results and take it to the line profile simulator and try to see if our simulations are actually like similar to observations, what would GMT see when it turns on? So we've been trying to look at the line profiles that GMT would see. So GMT will have a very nice spectrograph, IFU spectrograph, which was initially designed by Peter McGregor and now being led by Rob Sharp, which will have a high spatial as well as spectral resolutions. And for around, say, the kind of redshifts we're looking at, redshifts of 2, the spatial resolution will be around 150 parsec or so, which will be very good in finding out local features. And then with this, we can, by using our synthetic luminosity profiles, we can find the synthetic spectra that GMT would see. And this is the kind of thing we see. So this, what you're seeing is a side-on image of the jet. You see a large emission here because you're clouded by the clouds here. And these 3 panels are for 3 different locations of the spaxels. And this is oxygen 3 and H alpha. And this is the luminosity in oxygen 3 and H alpha. So the first thing to notice is that you have a double peaked profile. And the double peaked profile is because you have these 2 regions of the jet coming, like going out, like you're seeing it from the sides, and then they're going out. So one is the bow shock that is coming towards you, and one is the receding away. And that's for the double peak profile. And just to point out that this is also kind of similar to dual AGN kind of double peak profiles that people often see. But this is different. So if you have a good IFU resolution, spatial resolutions, you will actually be able to find out how these profiles will change at different locations. For example, if you look at these 2 panels, so this is in the center and this is somewhere up to the top, the relative heights of the lines have changed. This is because you're drilling through different materials with different clouds, densities, and that's why the different ratios. So if you have good high spatial resolution as well as spectral resolution, it will be a good test of the jet cloud interaction. So this is for a high redshift thing, but we have, with the current resolutions as well, we can target nearby galaxies where this jet interaction is going on. And then we've also been trying to understand what happens for the radio spectrum. So for example, we have this gigahertz peak spectrum where the radio spectrum turns over in the gigahertz region. And on one of the proposed model is free absorption. So basically you have synchrotron emission that is going along in line of sight. You have this dense cloudy medium. And then if you do the radiative line tracing, you'll get a kind of a turnover spectrum. So that is what we do. This is a model by Bicknell, Dopita, and O'Day in 97. This is opposed to the synchrotron self-absorption. This is not the SSA. This is the other version of it to try to fit the GPS spectrum. So when we do it for a jet, we kind of reproduce the kind of profiles that's similar to the observation. So these 2 plots show the jet at 2 different locations. The first note, these are for different simulations. So just let's focus on one of the colors, for example, the green one for one simulation. So first to notice the turnover frequency has shifted as the jet has gone through. This is because the jet is clearing its environment. It's really churning the environment around it, and that changes optical depth distribution around the cocoon of the jet. And also the slope has changed. And this is kind of similar to what Steve Tinke has recently found in his 2014 work, where these are observations of this source, PK 1718, 649, at different epochs. And he finds that there is a change in the turnover and as well as the spectra. So this is a case of a young radio source caught in action interacting with this medium. And if we have more observations like this, it will be very helpful. And summarizing, so if you let the gas relax, you'll have a filamentary structure through which the jets will pass through. The gas is swept outside by speeds of several hundred kilometers per second, but only a very small fraction actually leaves the potential of the galaxy. Low-power jets are more efficient in coupling with the ISM and then disturbing the ISM, but it really does not really drive the gas out, but really pumps in a lot of turbulence. And we will have observable features in optical line profiles from the shock-excited gas as well as from the radio, and we need more observations. Thank you.
Nice to know that observations aren't completely redundant. Time for a couple of quick questions, I think. Heino, do you want to go first?
Interesting to see the O3 lighting up. How much is that compared to what you would get from photoionization from the AGN itself? So what fraction of the jet power would go into O3 luminosity and what fraction?
Yes. So what we find is for the highest runs, about a few 5% of the jet luminosity goes into O3. A few tenths of percent, well, less than tenths of percent. And we don't have photoionization, so we couldn't compare with that.
You could make an assumption what the disk luminosity would be for the jet power.
Yeah, so about, say, 5 to 6% of the jet power goes into the OC in the emission region.
So given the new sort of huge windfall of observations that have come out, have you guys been able to compare to the observations? For instance, just do your simulations match what Chris Harrison was seeing in his O3 observations with, I think it was the VLT?
No, we have not compared with that observation, but the kind of galaxies we had in mind was exactly IC 5063, and then Nicole's galaxy in 2008's work. So we've been trying to tune our parameters for that. So the kind of results I showed here are just arbitrary ones which you have not compared. But we plan to take up more runs targeted at some of the galaxies so that we can pin down exactly the parameters. Because the emission, everything is depends very strongly on the kind of densities you have and jet power. So we need to tune the parameters to get a match with observations.
Right, we're going to have to leave it there, I'm afraid. Thanks, Dipanjan, again. So the last talk before the conference summary is coming up. Yuresh is talking about AGN jets in distant dusty galaxies.
Yeah, hello everyone. So I'm going to talk about the AGN jets in distant dusty galaxies, and more particularly the high-red radio galaxies. So you have already heard about that, how jets forms, and how radio galaxies evolves. So now I'm going to tell you that how to find the radio galaxies if you are given a large radio maps. So we are carrying out the survey from GMRT at 325 megahertz, and so in order to find these high-red radio galaxies, we are picking up ultra-steep radio spectrum sources, which are a tracer of high-red radio galaxies, and then we are looking at counterpart at optical near-infrared, mid-infrared bands. And what interesting, we are finding that we have a substantial population of compact steep spectrum sources residing in a dusty galaxies. So the question is that why to study high-red radio galaxies, and the reason is that they are different than the nearby radio galaxies. So they are hosted in massive galaxies with very high star formation rates. And typical star formation rate is something like 100 to 1000 solar mass per year. And they are likely to be progenitor of massive elliptical galaxies in the local universe. And they are also often associated with the overdensities like clusters and protoclusters. So in fact, powerful radio galaxies can be used as a tracer of overdensities. Yeah, so as I said that how to find out high-red radio galaxies in a survey. So if you look at the literature, the common strategy is that you begin with a wide and deep low-frequency continuum radio survey, and once you have a radio catalog, you extract out the probable high-red radio candidate using some criteria like ultra-steep radio spectrum sources or those radio sources which have a faint K-band counterpart. And once you have your probable candidates, you can go for the identification in optical and infrared band, and eventually you have to measure the redshift, either spectroscopic redshift or photometric redshift. Yeah, so it's like I've used this ultra steep spectrum criteria in order to find high-red radio galaxies, and this plot tells you that why the USS criteria is successful in order to find the high-red radio sources. So this is spectral index versus redshift, and you can easily note that all these sources which have a steep spectrum, it's like spectral index is steeper than -1.3, they are lying at redshift beyond 0.5. So one can ask that what can be the reason for this? So the conventional explanation is that one thing that most of the radio galaxies, they show a concave radio spectrum. So this is a radio spectrum of Cygnus A, which is a local radio galaxies. So you can note down that it's like once you go to higher frequency, the spectrum steepens. So if the same Cygnus A like radio galaxies, it had higher redshift. So because of the because of the K correction, the effective spectral index in observed frame would be steeper. But at the same time, there are galaxies, radio galaxies, which do not show this kind of curvature. You may see a kind of steep spectrum across the frequencies. So the explanation for these that they are likely to be lying in the denser environment, and where all these electrons at different energies, they lose energy, and the spectrum becomes steeper. So as I said that we are carrying out survey from GMRT. So these are the three fields which we have targeted: XMM LSS, Lockman hole, and ELS N1. So we already have a map of XMM LSS covering 9 square degree and reaching down to 160 microjoules at 325 megahertz. And we have something like 3,000 odd sources. Yeah. So in fact, the objective of this survey is much more larger than what I'm telling you, and which is basically to understand the covariation of star formation and AGN activity across the redshift. So this is 325 megahertz image at the background, and these are the footprints of different surveys. So we do have a far infrared and mid infrared surveys from the Herschel and Spitzer, and we also have a kind of two fields which have a deep coverage in optical and in near infrared. So this field is called VLA-VVDS. So this field does have a VLT deep survey from BMOS, and this is called Subaru X-ray deep field. So there is a deep Subaru optical data and also the deep X-ray data. So so far we have concentrated in these two deep fields. So what we did that we cross-matched 1.4 gigahertz sources and 325 megahertz sources, and we selected the sources with a steep spectrum. So here I'm giving the numbers. So this is a histogram of all these sources which are detected at 2 frequencies. And so we have taken only those sources which have a spectral index steeper than -1. So doing this, we are getting total sample of 160 sources. So ideally, I mean, you should have a kind of it's like flux densities across the frequencies, but here we are limited with the only 2 frequencies. So effectively, we are measuring a 2-point spectral index. Yeah, and so once we had this ultra steep radio sources, we looked at the counterparts in optical and near infrared. And as I said, that advantage is that these 2 fields are covered with the VLT and Subaru. So we have in the VVDS field, we have something like 10-band photometric data. So, and also there is a spectroscopic survey. So after looking at the optical counterparts, what we found that there are something like 74% sources which do have a redshift, either photometric redshift or spectroscopic redshift. And if you look at this is the redshift distribution. So we are picking up sources up to redshift 4, and in this Subaru field, something like 90% sources are having redshift. And if you look at this median redshift, so median redshift is something like 1.18, and in Subaru, because in Subaru we have a deeper optical data, I can give you an idea that R band magnitude is something like 27, and STSS goes 22. So it is something like 5 magnitude deeper than the STSS. So here the median redshift is 1.57, and these peaks were unexpected. But what we found that there are clusters at this redshift in XMM LSS, particularly the VLA-VVDS field, so that are giving rise these peaks. But in Subaru fields, we don't have a cluster, so we are getting a flat distribution there. Yeah, so if you look at the radial luminosity of all these sources, so we have a large fraction of FR2 type sources, and this is based on the luminosity, because there is large fraction of sources which appear a point-like sources. We don't have a morphology for those sources. So as I said, the median, if you look at the median, this is something like 10 to the power 25 watt per hertz. And but we also have some contamination from star-forming galaxies or radio-quiet AGN. Yeah. So next, obvious step is to look for the nature of these sources. So what we did that we used a diagnostic plot proposed by Norris and collaborators. So this is essentially you take the flux ratio at radio and mid-infrared at 3.6 micron, because we also have a these fields are covered by a Spitzer, so we do have a 3.6 micron counterpart. And so if you plot this flux ratio versus the redshift, so this allows you to segregate different kind of galaxies. So here you can see that all these the low redshift galaxies, which are basically the normal star-forming galaxies, they will have a very low flux ratio, and also at redshift there will be something like 0.1 or 0. But once they are radio loud sources, this flux ratio increases. So we are finding a large population at moderate redshift, ranging from 1 to 4, and this, if you look at, this is called sub-millimeter galaxies regime. So it seems that in these deep surveys, we are picking up sub-millimeter galaxies, but we're not picking up many powerful radio galaxies, which is expected because these we are covering something like 1 square degree. Yeah, so in total we are covering 1.8 square degree, and the sky density of powerful radio galaxies is not much. So yeah, so you can see only there are few powerful radio galaxies. Yeah, so now next question is that if they're not very powerful radio galaxies, what they are? So we also looked at the sizes. So you can see that there are something like 40% sources which do have they are typical radio galaxies, and you can we can have sizes. So they are something like 100 kiloparsec, this log scale. But at the same time, we have something like 50% unresolved sources. And so this population is quite interesting, because these appear like unresolved sources in GMRT and VLA images. So that allows you to put a kind of constraint on the size. So if you just take the kind of the synthesized beam size, so that gives something like 20 kiloparsec. So all these sources are are of less than 20 kiloparsec. So, and they also have a steep spectrum. So these can be called compact steep spectrum sources. And here you can see that all these sources are at higher redshift higher than 0.1. So if you really want to look at the morphology of these sources, you need something like sub-arc second or milli-arc second resolution, which you can achieve only from the VLBI or VLBA like experiments. So here I'll show you one example of this kind of population, that this is a galaxy called Iris, this number. So this is a compact steep spectrum source in the dusty galaxies. So total ultraluminous volumetric luminosity is something like 10 to the power 12. Elson. So this is a very star-forming dusty galaxies. And if you look at the flux ratio or the luminosity ratio in far infrared and optical band, this is 360. So which means that this is a heavily dusty galaxies, and this is a powerful galaxies. So I mean, with a GMRT or VLA, you will see this as a point source. But once you go to VLBI, which gives you a very high resolution, so you can see that this is a typical double lobe radio galaxies, and the total size is something like 1.7 kiloparsec. So we believe that most of our sources, which are CSS sources at redshift of 2 or 3 and residing in a denser environment, they are similar to this source. Yeah. So I mean, yes. So this is a kind of plausible scenario that these are kind of young radio sources, as recently as 10 to the power 4 years ago, and jets are flowing through the dense gas, and eventually it will heat up and dispel the circumnuclear dense gas. So eventually it will become a kind of full-fledged radio galaxies. So it seems that we are catching all these sources when they are going through a kind of transition phase, where you can see that intense starburst as well as radio activity is going on. Yeah, I'm done. Thank you.
Any burning questions? I think it's There's a question? Okay, yeah, we have time for a question because I think Roger's...
Not an expert in this field, but can you please comment on the fact that since you said that this could be that the jet has recently turned on, how do you, I mean, do you estimate the age of the source on the basis of synchrotron cooling timescale? How do you estimate that?
Yeah, so there's something called spectral aging measurements or dynamical aging measurements. So this is just an estimate. So even if you look at the size, and if you believe that this is a young ray, because there is other kind of sources which are called frustrated radio galaxies, so which haven't come out of the galaxy. So if you look at the dynamical time scale, that comes around 10 to the power 4 or so. But eventually, I mean, if you really want to measure the age, you need to have a kind of spectral aging. For that, you need a multi-frequency observation.
Do you think that these objects have some different properties, like in terms of black hole mass or accretion or all these things? Have you tried to look or compare these properties, or?
Not. I mean, if I look at the studies in the literature, they are intensely star forming, but the black hole mass is something like 10 to the power 8 solar mass.
So that's more or less
typical of radio loud AGN.
Okay, this is quite interesting. Yeah.
Okay, let's thank the speaker again. Right, so conference summary, here we go. What have we learnt?
Right. Okay, all right, great. Well, firstly, thanks to everybody for inviting me and everyone else here. It's been a wonderful meeting, and I've learned a huge amount, which may tell you more about my inattention of the past years, and so certainly that will be demonstrated in the upcoming attempt at summarizing. The subject, and it keeps on, it never gets away from it, is intensely taxonomic, shall we say. And of course, the categorization keeps on changing from one year to the next, and the acronyms keep on changing, and it's very hard to keep track of it. But one thing that has not changed is one of the earliest divisions or classifications there were, which is the Fanaroff and Riley classification. And I mean, people have already said a lot about it already. And I just sort of point out this is a rather short and snappy, in the polite sense, five-page article that makes a profound point. And in spite of everyone expecting it to being ephemeral when we got larger samples and the rest of it, I see absolutely no reason to look at it in any different way. They made a very simple point. It's remarkable, and it cries out for a physical explanation. A lot of what we're doing is there, and it's really been durable. And attempts to sort of elaborate and so on have less good than the original version. So this is Bernie, who I obviously knew as a fellow graduate student somewhat, and Julia Riley, who I knew somewhat earlier and somewhat better at that time, and I'm sad that she couldn't be here because I think she would have enjoyed this meeting. But at any rate, it was a very fine paper, and with a lot to add to it. Now, as we go on. Oh, sorry, I didn't want to go back one yet. My hand slipped. Okay, so as we go on, there's obviously been many other things that we've learned on the way, and you heard a bit of that from Tony Reedhead this morning. We've had many talks here. I should say this has been very hastily put together, almost in real time, and many pictures are missing from this presentation, and many names are missing from this presentation, and some of them put in the wrong place. Part of my problem was all of yesterday. I thought all of yesterday, I couldn't get into hold of yesterday's slides, and today's I was handling with an iPhone, but which was not totally satisfactory. So I missed out a lot of yesterday's talks. But at any rate, so some of these attributions are notional, but certainly Prajval gave us a very nice talk about blazars, and this was very important to understand that. You know, the subset of AGN with relativistic jets that were beamed towards us were going to be vastly overrepresented in complete samples. We call those blazars, and those have been split up nowadays into the lower pad BL lac objects that don't have bright emission lines, and they certainly, contrary to something that was said or may have misunderstood, certainly don't have quasars sitting underneath them, because the quasars are extremely luminous and they don't have these emission lines, although they can exhibit them some of the time, and that's important, and I'll return to that point. And then there's the brighter version of this, the flat spectrum radio quasars, and they've had other names over the years, and they seem to be sort of similar in their properties and also distinctly different. Something we've heard here, and I was very impressed by this talk, was, it used to be a thing we say that, the radio sources are associated with elliptical galaxies and the spirals don't exhibit them, but we know that spirals can be radio sources, they're not radio silent, but they can also exhibit jets, as we saw rather nicely from the work, and it's very nice to see GMRT contributing in this very special way and seeing these very rare spiral jets and sort of crying out for an explanation. And we heard many good speculations there, and there's a very happy godfather of GMRT seeing these results. So the other sort of type of jet, and it's consciously was underemphasized this meeting, are the ones associated with galactic objects, the gamma ray bursts, the pulsars, the protostars, and so on. There's certainly jets, there are more of them, of course, and there are lessons to be learned from and to those classes of objects, as we saw particularly this morning in SS433. I don't have a picture of it, I couldn't get one of that, so let me sketch it for you. It sort of looks a bit like that, I think, and then there's a 3 there like that, and a 3 there like that, and then there's a, if I get right, there's a sort of 4 there like that, and so I couldn't get the proper image, but it looks pretty much like that. I was told that joke translates into Urdu, but I'm not if I did that on my side, but anyway. But these are really quasars for the impatient, and the extent it's just a scaling with mass. We can learn a huge amount about the long-term evolution of quasars by looking at the microquasars. And in fact, in the information paper, would go the other way. And this is so important. And then we saw SIG-X3. We saw the sort of evidence presented there for precession, and there are other sources, of course, that do this. Some associated with different classes of objects. And then the SIG-A, we saw some discussion of the possibility that was a precessing source. And then there's also the binary black holes, which have been invoked. And again, this is where there's, there have been 3 or 4 recent claims in the literature over the past year that we discovered binary black holes in active galactic nuclei. And one of the alternative possibilities, well, 2 alternative possibilities. One that is just red noise, and that's real and present danger. That's the sort of noise that keeps me awake at night. But another one is that you're looking at a quasi-periodic oscillation, which of course is a well-known phenomenon. This scales with a 10 Hertz quasi-periodic oscillation associated with an AGN. So you clearly need much more data in order to really sign off on the fact that you're seeing a binary black hole. But the scaling with the microquasars is obviously a very good way to do this. Another sort of classification which has been here, and I don't know, I have to ask our chair whether it's a lurg or a leg, and no, it'll be something different next meeting, but we all know what it means, and that at least the general thought has been there for a long time, the excitation, the high excitation lines. And then something came up this morning which, it's sort of blindingly obvious, and I think everybody knows this, that when we look at, you can say that it's part of the unification sort of story was